All right, we're going to look at several different equations, chemical equations. We're going to predict the products and then look at this equation. We're going to balance it and then write the total ionic or the complete ionic equation as well as the net ionic equation. All right, so first of all here, when we're writing the products, all right, we can look at this and we have two ionic compounds, right? The calcium nitrate, we have calcium ion, we can kind of split that between the cation and the anion, and we can split this one between the cation and the anion. All right, so the only possible products are, because this this polyatomic ion isn't going to break apart. All right, that would be a special kind of reaction. It might do that, but for the types of reactions that we'll be predicting products for, we're going to leave any ions the same, and the only thing that's going to happen is the cation from the one compound will join the anion from the other. And so they kind of switch partners. The calcium, instead of being with nitrate, it'll be with the fluoride. And the potassium, instead of being with the fluoride, will be with the nitrate. Okay, so those will be our products. The calcium, but remember, the calcium has a +2 charge. Okay, so we're not necessarily looking at these subscripts, so we can't just put CAF because it's KF. That's when it's with potassium. There's one fluoride, but when it's with calcium, calcium has a +2 charge. It's in that second column on the left, and so that gives it a +2 charge. And the fluorine is one column away from the noble gases, so it has a -1 charge. All right, so that means I need 2 fluorine ions for the one calcium ion. Okay, so that's one product. And then we have potassium and nitrate. Right? Again, the potassium in the alkali metals column, the first column to the right of the noble gases, if you will, it has a +1 charge. The nitrate has a -1, so that's just KNO3. All right, so those are our products. Now we're going to balance this equation. Okay. So we can balance this by the ion. We don't have to balance each individual element. Since NO3 is the same there as it is over here, I can just look at this and say, okay, I have 2 nitrate ions, so I'll have 2 nitrate ions here. Okay, and that gives me 2 potassium ions, which I will balance in that way. That gives me 2 fluoride ions, which I have there, so fluoride is balanced, and then I check calcium is balanced as well. Okay, so this equation is now balanced. So this is what we would call the molecular equation. Okay, that's where it's just written in the regular notation. But now we want to look at this and say, well, which of these compounds, if I put this in water, which of these compounds will dissolve? And which one will remain as a solid? Okay, and so that there are some general rules that we can reference in determining whether different compounds will be soluble or not. And one of those rules, depending on your textbook, you may have slightly different rules because they're not hard and fast rules, but there are some general guidelines, such as all compounds containing nitrate ions are soluble. Okay, and there's no exceptions to that rule. So calcium nitrate is no exception. That means when this is in solution, that is when we mix it with water, it dissolves. And when it dissolves, the calcium ions separate from the nitrate ions. So I'm going to write this as calcium, and this is not just calcium metal, okay? It is the calcium ions, right? And these require water to separate, okay? So that's going to be aqueous. The calcium ions are now separate from the nitrate ions, also aqueous there. Any ion is going to be an aqueous solution because it's the water that is pulling those apart or allowing that to dissolve. Okay, but let's pay attention to this. We have two nitrate ions, so when they separate, I have two separate nitrate ions. So that's going to come out like that. Okay. Now I look at potassium fluoride, and I'll reference the solubility tables, and you'll probably have a reference that says potassium compounds are soluble. Any of those group 1 compounds, sodium, potassium, lithium, and as well as ammonium, those are all soluble compounds. No exceptions. Okay, so that one's going to be soluble as well. Now I have 2 Kf formula units there, so I'm going to have 2 potassium ions that are aqueous and 2 fluoride ions. That 2 goes to both of those ions. Okay, so there is my reactant mixture. Now what happens, I will determine in the same way, identifying whether these are soluble or insoluble. Okay, now this calcium fluoride, again, depending on what textbook you have, you may see different rules. Some may be more complete than others. In this particular textbook that I am referencing, the one we are using here at Cleveland State, this is TRO, the second edition for chemistry, a molecular approach. And on page 149, it has some solubility tables, but we look at this and we don't find any calcium referenced in the table, nor do we find any fluorine or fluoride ions referenced in the table. Okay, so we don't really have a good reference in our solubility tables for this textbook. However, if you look in other textbooks, you may find more complete information. And what we would find is a rule saying that fluoride-containing compounds are generally soluble. Okay. However, there are some exceptions. And a list of exceptions: magnesium, calcium, strontium, barium, lead, so calcium is one of those exceptions, which means calcium fluoride is insoluble. So we write it together, okay? It is a solid. We write it exactly how it appears in the solution. If it dissolves, that means the ions separate. If it's insoluble, that means the ions are still together, so we write it as a solid. Okay? So this particular example is not one that I would expect you to be able to use with the tables in the TRO textbook, but based on other information, we can do this problem as well. Okay, and then here we have potassium nitrate, definitely a soluble compound. Nitrates are soluble. Potassium containing compounds are soluble. Let's not forget that 2 in front. That means I have 2 potassium ions. Those are aqueous because it's in water. That's what pulls them apart or allows them to separate. I also have 2 nitrate ions. Okay? Don't forget to write those charges. Okay? We don't have any charge on the compound, but on all of the ions we will have charges. Okay? So here is my complete ionic equation. All right? And what we need to do now is to look at this and say, okay, what ions are the same on the left as on the right? What we find is, we just saw the 2 nitrate and the 2 potassium ions there. Those will cancel out, and in the end I have calcium plus 2 fluoride ions. Okay. And if we have distributed all of our coefficients and everything properly, this will always remain balanced. And this should be a solid here. Okay, so that would be the net ionic equation, showing just what is actually chemically happening there, excluding the stuff that isn't really participating in any reaction. We call these the spectator ions because they're just kind of sitting back and spectating on the reaction. All right, so let's move on and do some of these others here. I'm going to do the same process. I'll go through these ones a little bit quicker. We split them apart, cations and anions, and then the cation will join up with the anion from the other compound. They kind of switch pairs. We call that a double displacement. All right? So the barium joins with the sulfate. Barium is positive 2, sulfate negative 2, so that's BaSO4. Then we have hydrogen joining with chlorine. Hydrogen is a +1. Chlorine is a -1. So that becomes HCl. Okay. We look at our solubility tables to identify whether this is a soluble compound. And we'll find that chlorides are generally soluble. They do have some exceptions. Silver, mercury 1, or lead 2. Barium is not one of those exceptions, so that would be soluble. So when we write it, we write the ions separated because that is their soluble form. Okay, not forgetting that that we have 2 separate chloride ions. Okay, now we have this compound, sulfuric acid. Okay, when we have acids in these equations, we can't look at solubility tables because it's an acid. Okay, so what we do is we say, all right, what I'm really wanting to know, how should I express this in my equation? Does it separate into ions, where I have hydrogen ions and the sulfate ions, or does it remain together as a molecular unit? Okay, so you will be referencing a table of strong acids and weak acids. Okay, there are actually only about 6 strong acids, and you should have those memorized. Okay, a strong acid is an acid that will dissociate. Okay, and sulfuric acid is one of those strong acids. it dissociates into hydrogen ions and sulfate ions. Okay? And technically it only gives up one hydrogen ion and then has a hydrogen sulfate ion in addition, but then that hydrogen sulfate can also give up another one. So the net effect is that you have two hydrogen ions and a sulfate ion. Okay? Because it's a strong acid. In this case, we're not looking at the solubility tables and saying, well, are sulfate ions or sulfate containing compounds soluble? Even though it says that, they are, but that is when they're with some kind of a metal ion or ammonium or something, right? Acids are different. We have to look if it's a weak acid or a strong acid. This is a strong acid, so it dissociates, okay? A weak acid would remain in its molecular form. All right, so here are our reactants. Now let's look at the products. Okay, barium sulfate, sulfate-containing compounds. You'll find those on the soluble side of your solubility tables. They're usually soluble. However, there are some exceptions, and in fact, barium is one of those exceptions. So barium sulfate is an insoluble compound, meaning we leave it together. Those ions do not separate in the water. So it's a solid. All right? Then we look at HCl. Again, it's an acid. Okay? And I just realized I haven't balanced this equation, because if we balance it, you see we need a 2 in front of that HCl. All right? So here it's a strong acid, one of those ones you just kind of reference them or memorize them. And so we have 2 hydrogen ions, which are aqueous, and 2 chloride ions, also aqueous. All right? So here we look, and that's our complete ionic equation. And now we're going back and we're going to cancel those spectator ions. Right? And that will leave us with the net ionic equation, the barium ions plus the sulfate ions, aqueous, to produce the barium sulfate solid. Okay, so the barium ions from the barium chloride, when you mix these two together, they join up with the sulfate ions that are released in the sulfuric acid, and then the water can't keep those ions separate, so they join together like magnets and form the barium sulfide, or rather sulfate solid. All right, let's do this next one. Okay, same process. Here you recognize that acetate ion. That's how you know to split it here and not somewhere in the middle. You recognize, oh, that's the acetate ion, and I have a hydrogen ion in front. Okay, so this is another acid. So just like in the previous case, we're going to have to ask ourselves, is that a strong acid or a weak acid? Okay. This one, even though this is a base, we don't have a special table with bases, we can reference this as a solid, or rather a salt, and the hydroxides are just a basic salt, essentially. And so you'll find hydroxide ions under the insoluble part of the table, with some exceptions. Okay, but I'm getting ahead of myself a little bit. We need to predict our products. Potassium will join up with the acetate, +1, -1, K C2H3O2. The hydrogen will join up with the hydroxide, and you have H2O. Okay. So now we have our complete equation. One ion of each on both sides, so we are balanced. Okay. So now I was saying that normally hydroxide ions are soluble, or rather are insoluble. However, potassium salts are soluble without exception. Therefore, the potassium ions, as well as lithium and sodium, are exceptions to the rule that hydroxides are insoluble. Okay, so this is a soluble compound, and so we have the potassium ions. When we put this in water, we just put the water as aqueous, plus hydroxide ions. Okay. Then now we're looking at the acid. Right? Is this a strong acid or a weak acid? Well, there's only about 6 strong acids that I have mentioned, or as I have mentioned before, and we've seen 2 of them already: sulfuric acid, hydrochloric acid. There's also hydrobromic acid, HBr, hydroiodic acid, HI, and then there's nitric acid and perchloric acid. Okay, those are the 6 main strong acids that we will encounter in this general chemistry course. Any other acid is a weak acid, okay, including acetic acid. Right? So that means this is a weak electrolyte. Right? When it's a weak acid, it's a weak electrolyte, meaning it doesn't dissociate. The hydrogen ions don't dissociate from the acetate ions to a significant extent. Right? Which means when we write this in our equation, we write it in its molecular form. Okay? But this is in water still. Acetic acid is a liquid, all right, but it's in the water, and so we would put aqueous with that. Okay. On the product side, we're looking at potassium acetate, and this is going to be a soluble compound. Potassium containing salts are soluble, as well as acetate ions. Okay, so we would write this like so, okay, separating those. Then we have water, all right? Well, water is just water, okay? It does not dissociate in water, so that one, and this one we don't put aqueous because it's water, so it's a liquid. All right, that would be redundant if we said aqueous. The water is with water. It's already water. So that's all we do with that one. Now we look at this. That's our total ionic equation, and we want to cancel out any spectator ions. Now in this case, we only have one, the potassium ion. Okay, so we have hydroxide ions plus acetic acid. These are all of the components that actually participate in the reaction. Okay, only the potassium ions in this example do not really participate in the reaction here. Okay, so what we find is that the hydroxide ions essentially steal away a hydrogen from the acetate, or rather from the acetic acid to form acetate and water. Okay, that is the net ionic equation. All right, getting a little bit cramped on space, but we'll continue here. Strontium acetate plus lithium sulfide. Okay, same process. We'll split this up into cation and anion for each of these ionic compounds. Do our double displacement. Strontium sulfide, +2, -2, so that's just going to be SRS. Not talking about an airbag. Okay, and we have lithium with the acetate, +1, -1. Remember, we're not using these coefficients. That's when it was with the sulfide or with the strontium. We're using it when lithium is with the acetate. Okay, and it goes together 1 to 1 there, but we need to balance it. Okay, and that's where that 2 comes in. Okay, now we have our balanced equation. Let's consult our solubility tables, and you'll find here it'll list acetate in the soluble section, and we look for exceptions. Well, there are no exceptions to acetate containing compounds, so this is a soluble compound. So we have the strontium ions plus 2 acetate ions. Right? And then we look at the lithium sulfide. Well, lithium salts are soluble. Again, no exceptions. If you look at the sulfides, you'll find sulfides are usually insoluble. However, one of the exceptions is that first group of elements, lithium, potassium, sodium, the group 1 elements, the alkali metals. Okay, so here this is going to separate into 2 lithium ions, and remember the ions are always aqueous because it requires the water in order to separate it. If there's no water, it remains a solid. As soon as you put that in water, that's what enables it to dissociate. And then we have the sulfide ions. Okay. All right, and then we look. Sulfides are generally rather insoluble. So and this is from our table. We're just referencing a table, and bear in mind the table is a simplification. It's really a spectrum. You don't have something that is just completely insoluble and something that's completely soluble. It's a spectrum. There's things that are very soluble, more soluble, slightly soluble, and very little soluble. And this is just kind of the tables give you an idea. Well, these compounds are usually soluble, or they're the most soluble. So when we say this is a soluble compound, what we're saying is we're not saying that it will dissolve to any extent in water, but at least for most purposes, a significant portion of it will dissolve, okay, at a significant concentration. So just bear in mind, the tables are a simplification. It's really a spectrum of from soluble to very, very insoluble, where only a teeny tiny fraction of the molecules will actually dissociate. All right, but if we look at the sulfides, we check for the exceptions, and here, again, depending on what textbook you're referencing or what tables you're looking at, you might find differing information. The 2 textbooks that I have referenced actually show different information. And so you're limited by what tables you have, and that would be taken into account, in homework and such, on tests and that sort of thing. All right. But in the textbook that we're using with TRO, it shows that when sulfide ions are paired with calcium or strontium or barium, it makes a soluble compound. Okay, so strontium sulfide is actually a soluble compound. So we're going to write it with those ions separated. Okay. Finally, at the end, we have one last soluble compound. We know that's soluble because the lithium, as well as the acetate, all of those salts are soluble, again, coming from the table. Okay? Make sure you remember all of those charges, the coefficients it distributes to the lithium as well as to the acetate, but we have to put our charge, and then the subscripts are typically present as well. All right, now what do you notice about this one? Okay, here we have strontium ions on the left, strontium ions on the right. They cancel. We have acetate ions over here, 2 acetate, and then we have 2 acetate ions over there. Those cancel. We have sulfide and lithium, the 2 lithium ions, and they cancel. Is there anything left? There's nothing left. All right? So we conclude from this then that there's no net ionic equation, right? This is a total ionic equation, and everything on the left was just the same as what it was on the right. We canceled out the spectator ions, and everything was a spectator ion. That means there was no reaction. Okay? Now, as I was mentioning in the previous textbook that we were using before, the sulfide, it didn't show strontium as an exception to the insoluble rule for sulfides, in which case we would have left that together and it would have showed a reaction. Okay, but in a case like this, and the reason for that is because really the strontium sulfide it's soluble, but it's not extremely soluble. All right. Remember, it's a spectrum, and these rules are just to give us the general idea, but it's not a hard and fast, completely soluble versus completely insoluble. It's a spectrum, and it depends on where you divide that line. There's a little bit of subjectivity there. Okay, so it's your answers may vary depending on the tables that you're using. Okay, but the net ionic equation kind of zooms into just what's happening. We saw in this previous example, it showed that the barium ions were joining with the sulfate ions. Everything else was just kind of in the background. Okay, and in this case, everything is just kind of in the background. They're just sort of hanging around in the solution. There's not really anything happening, so that would be no reaction. Okay, let's look at one more example. We have calcium hydroxide and sodium phosphate. Okay, follow our same routine. We split this up into the anions. To predict our products, we swap the pairs. Calcium will join with phosphate, and again, avoid the temptation to just write, CaPO4, because what's the charge of calcium? +2. It's in that the alkaline earth metals, the second column to the right of the noble gases, if you will. And then phosphate, you know, is a -3. Okay, so +2, -3. My actual formula will look like this. Okay, Ca3PO4 2. So don't just use what it came with. You have to discover what that formula should be when it unites with the other ion. Okay, sodium and hydroxide. Sodium is a +1, hydroxide a -1, so they go together 1 to 1. All right, now we balance this equation, and we have 3 calcium ions here, so I need 3 over there. When you're balancing, you want to start with the one that has the high subscripts. Okay, and then that gives us 6 hydroxide ions, so I need 6 hydroxide ions here. That gives me 6 sodium ions, so I need 6 sodium ions here. 2 times 3 will give me that, and that gives me 2 phosphate ions, and they're ion balanced. All right, so that's the molecular equation. Now let's check our tables and find out what is soluble, what is insoluble. Calcium hydroxide, if we look under the hydroxides, we find they are generally insoluble. We check the exceptions, and it says when hydroxide pairs with calcium, among others, the resulting compound is slightly soluble. Okay, so we would say calcium hydroxide is slightly soluble, right? And again, depending on what tables you're referencing, some will say slightly soluble, some might call it soluble, some might not include that with the soluble category. It's kind of in between there, right? But we'll say, okay, if it's slightly soluble, then at least some of it is going to be dissolved, and I can write it in the separated form. Okay, but I might, and I need to remember the coefficients here. I have 3 calcium ions, and then how many hydroxide ions? I'll have 6 separate hydroxide ions. Okay, so they get distributed because they all fall apart. Okay, I have 2 hydroxide ions, they fall apart from the calcium, and I have 3 of those all together, so all taken together I have 6 hydroxide ions. Okay, then we have sodium phosphate, and sodium ions are all soluble, no exceptions. This is a soluble compound. When this breaks apart, I have 3 ions here, but I have 2 of these units, so I have a total of 2 times 3 is 6 sodium ions, and these are all aqueous. Right? And then I have 2 phosphate ions. Okay, also aqueous. All the ions are aqueous, so that is a common subscript there. All right, now we check the calcium phosphate. If we look under phosphates, we'll find that phosphates are generally insoluble. We check the exceptions. Calcium is not an exception. The only exceptions to that rule are ammonium ions and the group 1 ions, sodium, potassium, lithium, etc. All right, but calcium is not an exception, which means when I put this in water, nothing happens. It remains a solid. Okay, so I write it just the same, the way it appears in the when you actually do this. It stays as a solid. Those ions do not separate. Then I look at the sodium hydroxide. Even though it's a base, again, bases we can treat just as regular salts. Okay, it's the acids that we look to consider whether they're strong or weak. But the sodium hydroxide, because sodium salts are soluble, that sodium hydroxide we will write in the separated form. Okay, again, 6 sodium ions, 6 hydroxide ions. Don't try to separate the polyatomic ions. You leave those together. Polyatomic ions won't separate in the solution, but the ions themselves separate from each other. Okay, so that's our complete ionic equation. Now let's cancel the spectator ions. Okay, sodium and hydroxide, sodium and hydroxide, 6 of each. Those will be my spectator ions. And what I have is 3 calcium ions that come from my original calcium hydroxide. They will join up with 2 phosphate ions that came from my sodium phosphate, and it will produce the calcium phosphate solid. Right? There is the net ionic equation telling you just specifically what is happening in that reaction, not looking at the other spectator ions. All right? So I hope this has been helpful practice in writing net ionic equations and total ionic equations, as well as writing products to double displacement reactions and balancing the equations. Just remember, there's a lot of little details that are easy to forget or to skip over. Write those charges, distribute the coefficients as appropriate, through both those ions. Write your states of matter, and then when you're predicting products, make sure you check the charges when you're writing your new formulas. Okay?